An electrolyte is a substance that produces an electrically conducting solution when dissolved in a polar solvent, such as water. The dissolved electrolyte separates into cations and anions, which disperse uniformly through the solvent. Electrically, such a solution is neutral. If an electrical potential is applied to such a solution, the cations of the solution would be drawn to the electrode that has an abundance of electrons, while the anions would be drawn to the electrode that has a deficit of electrons. The movement of anions and cations in opposite directions within the solution amounts to a current. This includes most soluble salts, acids, and bases. Some gases, such as hydrogen chloride, under conditions of high temperature or low pressure can also function as electrolytes. Electrolyte solutions can also result from the dissolution of some biological and synthetic polymers, termed polyelectrolytes, which contain charged functional groups. A substance that dissociates into ions in solution acquires the capacity to conduct electricity. Sodium, potassium, chloride, calcium, and phosphate are examples of electrolytes, informally known as lights. In medicine, electrolyte replacement is needed when a patient has prolonged vomiting or diarrhea, and is a response to strenuous athletic activity. Commercial electrolyte solutions are available, particularly for sick children and athletes. Electrolyte monitoring is important in treatment of anorexia and bulimia. Etymology. The word electrolyte derives from the Greek lytos, meaning able to be untied or loosened. History. Svante Arrhenius put forth, in his 1884 dissertation, his explanation of the fact that solid crystalline salts dissociate into paired charged particles when dissolved, for which he would win the 1903 Nobel Prize in Chemistry. Arrhenius' explanation was that in forming a solution, the salt dissociates into charged particles, to which Michael Faraday had given the name ion many years earlier. Faraday's belief had been that ions were produced in the process of electrolysis. Arrhenius proposed that, even in the absence of an electric current, solutions of salts contained ions. He thus proposed that chemical reactions in solution were reactions between ions. Formation. Electrolyte solutions are normally formed when a salt is placed into a solvent such as water and the individual components dissociate due to the thermodynamic interactions between solvent and solute molecules, in a process called solvation. For example, when table salt, NaCl, is placed in water, the salt dissolves into its component ions. According to the dissociation reaction NaCl Na plus Cl-, it is also possible for substances to react with water, producing ions. For example, carbon dioxide gas dissolves in water to produce a solution that contains hydronium carbonate and hydrogen carbonate ions. Molten salts can also be electrolytes, as for example, when sodium chloride is molten, the liquid conducts electricity. In particular, ionic liquids, which are molten salts with melting points below 100 degrees Celsius, are a type of highly conductive non-aqueous electrolytes and thus have found more and more applications in fuel cells and batteries. An electrolyte in a solution may be described as concentrated if it has a high concentration of ions, or dilute if it has a low concentration. If a high proportion of the solute dissociates to form free ions, the electrolyte is strong. If most of the solute does not dissociate, the electrolyte is weak. The properties of electrolytes may be exploited using electrolysis to extract constituent elements and compounds contained within the solution. Physiological importance. In physiology, the primary ions of electrolytes are sodium, potassium, calcium, magnesium, chloride, hydrogen phosphate, and hydrogen carbonate. The electric charge symbols of plus and minus indicate that the substance is ionic in nature and has an imbalanced distribution of electrons. the result of chemical dissociation. Sodium is the main electrolyte found in extracellular fluid and is involved in fluid balance and blood pressure control. All known higher life forms require a subtle and complex electrolyte balance between the intracellular and extracellular environment. In particular, the maintenance of precise osmotic gradients of electrolytes is important. Such gradients affect and regulate the hydration of the body as well as blood pH, and are critical for nerve and muscle function. Various mechanisms exist in living species that keep the concentrations of different electrolytes under tight control. Both muscle tissue and neurons are considered electric tissues of the body. Muscles and neurons are activated by electrolyte activity between the extracellular fluid or interstitial fluid and intracellular fluid. Electrolytes may enter or leave the cell membrane through specialized protein structures embedded in the plasma membrane called ion channels. For example, muscle contraction is dependent upon the presence of calcium, sodium, and potassium. Without sufficient levels of these key electrolytes, muscle weakness or severe muscle contractions may occur. Electrolyte balance is maintained by oral, or in emergencies, intravenous intake of electrolyte-containing substances, and is regulated by hormones. In general, with the kidneys flushing out excess levels. In humans, electrolyte homeostasis is regulated by hormones such as antidiuretic hormone, aldosterone and parathyroid hormone. Serious electrolyte disturbances, such as dehydration and overhydration, may lead to cardiac and neurological complications and, unless they are rapidly resolved, will result in a medical emergency. Measurement of electrolytes is a commonly performed diagnostic procedure, performed via blood testing with ion-selective electrodes or urinalysis by medical technologists. The interpretation of these values is somewhat meaningless without analysis of the clinical history and is often impossible without parallel measurement of renal function. Electrolytes measured most often are sodium and potassium. Chloride levels are rarely measured except for arterial blood gas interpretation, since they are inherently linked to sodium levels. One important test conducted on urine is the specific gravity test to determine the occurrence of electrolyte imbalance. Rehydration in oral rehydration therapy. Electrolyte drinks containing sodium and potassium salts replenish the body's water and electrolyte levels after dehydration caused by exercise, excessive alcohol consumption, diaphoresis, diarrhea, vomiting, intoxication or starvation. Athletes exercising in extreme conditions that do not consume electrolytes risk dehydration. A homemade electrolyte drink can be made by using water, sugar and salt in precise proportions. Pre-made preparations are also available commercially, and also for veterinary use, like Electrolyte. Electrolytes are commonly found in fruit juices, coconut water, sports drinks, milk, nuts, and many fruits and vegetables. Electrochemistry. When electrodes are placed in an electrolyte and a voltage is applied, the electrolyte will conduct electricity. Lone electrons normally cannot pass through the electrolyte. Instead, a chemical reaction occurs at the cathode, consuming electrons from the anode. Another reaction occurs at the anode, producing electrons that are eventually transferred to the cathode. As a result, a negative charge cloud develops in the electrolyte around the cathode, and a positive charge develops around the anode. The ions in the electrolyte neutralize these charges, enabling the electrons to keep flowing and the reactions to continue. For example, in a solution of ordinary table salt in water, the cathode reaction will be 2H2O plus 2E minus 2OH plus H2, and hydrogen gas will bubble up. The anode reaction is 2NaCl2 Na plus Cl2 plus 2E minus, and chlorine gas will be liberated. The positively charged sodium ions Na plus will react toward the cathode, neutralizing the negative charge of O minus there, and the negatively charged hydroxide ions O minus will react towards the anode, neutralizing the positive charge of Na plus there. Without the ions from the electrolyte, the charges around the electrode would slow down continued electron flow. Diffusion of H and O- through water to the other electrode takes longer than movement of the much more prevalent salt ions. In other systems, the electrode reactions can involve the metals of the electrodes as well as the ions of the electrolyte. Electrolytic conductors are used in electronic devices where the chemical reaction at a metal-electrolyte interface yields useful effects. In batteries, two materials with different electron affinities are used as electrodes. Electrons flow from one electrode to the other outside of the battery, while inside the battery the circuit is closed by the electrolyte's ions. Here, the electrode reactions convert chemical energy to electrical energy. In some fuel cells, a solid electrolyte or proton conductor connects the plates electrically while keeping the hydrogen and oxygen fuel gases separated. In electroplating tanks, the electrolyte simultaneously deposits metal onto the object to be platted, and electrically connects that object in the circuit. In operation hours gauges, two thin columns of mercury are separated by a small electrolyte fill gap, and, as charge is passed through the device, the metal dissolves on one side and plates out on the other, causing the visible gap to slowly move along. In electrolytic capacitors, the chemical effect is used to produce an extremely thin, dielectric, or insulating coating, while the electrolyte layer behaves as one capacitor plate. In some hygrometers, the humidity of air is sensed by measuring the conductivity of a nearly dry electrolyte. Hot, softened glass is an electrolytic conductor, and some glass manufacturers keep the glass molten by passing a large current through it. Solid electrolytes. Solid electrolytes can be mostly divided into four groups. Gel electrolytes. They closely resemble liquid electrolytes. In essence, they are liquids in a flexible lattice framework. Various additives are often applied to increase the conductivity of such systems. Dry polymer electrolytes. They differ from liquid and gel electrolytes in the sense that salt is dissolved directly into the solid medium. Usually it is a relatively high dielectric constant polymer and a salt with low lattice energy. In order to increase the mechanical strength and conductivity of such electrolytes, very often composites are used, and inert ceramic phase is introduced. There are two major classes of such electrolytes: polymer in ceramic, and ceramic in polymer. Solid ceramic electrolytes, ions migrate through the ceramic phase by means of vacancies or interstitials within the lattice. There are also glassy ceramic electrolytes, organic ionic plastic crystals. They are a type organic salts exhibiting mesophases, in which mobile ions are orientationally or rotationally disordered while their centers are located at the ordered sites in the crystal structure. They have various forms of disorder due to one or more solid-solid phase transitions below the melting point and have therefore plastic properties and good mechanical flexibility as well as improved electrode-electrolyte interfacial contact. In particular, protic organic ionic plastic crystals, which are solid protic organic salts formed by proton transfer from a Bronsted acid to a Bronsted base and in essence are protic ionic liquids in the molten state, have found to be promising solid-state proton conductors for fuel cells. Examples include 1,2,4-triazolium perfluorobutane sulfonate and imidazolium methanase sulfonate.